So thank you to listening to me. So in this talk, I would like to do something quite different because I am a physicist. And so in this talk, I would like to discuss about some applications of geometry and geometrical formalism for physical systems, which can be useful for applications in physics and beyond in engineering. So in this talk in particular, I would like to focus on dissipative systems, because dissipative systems are systems which are common in physics and interesting for many applications. And when you are looking to mechanical systems, dynamical systems, and some things where we typically want to use a lot of geometry, and in particular infinite dimensional geometry for fluids. And so the question is how to put dissipations into this kind of geometrical formalisms for physical systems. So in this talk, I would like to start just by just basics that you probably already all knew, which is just Hamiltonian dynamics, which is the basics of how to use geometry to do physics. So this Hamiltonian approach was developed in the 19th century, but physically it's not new compared with Newtonian dynamics. It's, however, a reformulation of Newtonian dynamics, which can be useful because it uses geometrical tools. So because we have this geometrical approach, we can get more insights on new ways to apply, to attack some physical system with this new approach. But it's also important because it's a starting point for many things, in particular for statistical physics, where you will want to work in the phase space to be able to question things like ergodicity and then to do some statistical physics as we like to do in physics, but also for quantum physics, because it's from this Hamiltonian perspective that you want to do quantization to go into the quantum world. And finally, it's also useful for numerical applications, because when you do numerics, as you know, you want to make discretization passes, and for that, it's useful to have an Hamiltonian approach to be able that you will conserve some properties like the conservation of energies, and then avoid some divergences which are very common in dynamical systems numerically. So this Hamiltonian approach is very useful for many applications. And this can apply to many systems, for example, fluid systems. So on the left, you have a usual turbulent fluid dynamics. And on the right, you have a star where you will have a magnetic field because you have a plasma, and then you have plasma dynamics with can be described with MHD. So these two kinds of systems, you have equations to describe them. For example, the first one, you have the Euler equations. You can use these equations, which is just a reformulation of Hamiltonian dynamics going into a new set of variables. And then you will get a pressure term, which is just a Lagrangian multiplier, which imposes that you preserve volume. You can also add some magnetism, for example, for plasma. And then you will add, in addition, an equation for the magnetic field. So you have a new set of equations, and you couple everything. That's what we call MHD for magnetohydrodynamics. So these two kind of equations are equations in fluids that you can write geometrically in an Hamiltonian fashion, and which are very useful for many physical applications. However, in these two kind of systems, there is something which is missing, which is dissipation. In any of these systems, which is Euler equations where you don't have viscosity, or MHD when you don't have resistivity, you don't have any way of relaxing momentum and energy in this kind of systems. However, in physics, relaxation processes, and in particular dissipation, they are very important and key in many applications. So of course, when you are at very large scales, on some limits, you can sometimes neglect this kind of dissipations. But when you are close to the edges, close to the boundaries, or at smaller scales, it's no longer possible to neglect dissipation, which becomes very important in the dynamics. So why we don't put dissipations to go from Euler to Navier-Stokes, or to go from perfect to dissipative MHD usually in this kind of schemes? Firstly, because it's complicated. It's much more complicated to handle this from an analytical point of view. And secondly, because it's not Hamiltonian anymore. Indeed, the Hamiltonian formalism is powerful, but it does not apply to dissipative systems, because by construction, the Hamiltonian dynamics is made to be energy conservative, and then not to include any dissipation, which will be a loss of energy for your system. So it means that all these kind of dissipative dynamics, you cannot treat them with an Hamiltonian dynamics as usual. So when we do geometry of Hamiltonian dynamics, we have already restricted a lot the kind of physical systems we can apply to. So the goal of this talk will now to be to try to discuss some tricks, some ways to include some dissipation in this Hamiltonian or Hamiltonian-like dynamics. So for this, we will discuss two options. The first one will be to go from a Poisson bracket, so from a symplectic form into a more general form, a more general bracket. And this is what people call the metriplectic or generic formalism. And second options we will discuss will be to include singularities in the system. So we'll keep an Hamiltonian-like geometry, but we'll allow some singularities, and we'll see that singularity will play the role of including some dissipation in the systems. So for the first part, let us discuss the metriplectic formalism. So if I go back from basics, we want to work in a phase space. So we have a space of configuration plus a space where you will allow the velocities to be working. And then we want, so for example, for a fluid, it will be the set of velocity fields. And we want to allow functionals on it. So for example, for physics, we want to include the energy functional, which will describe the energy of the system in a particular state. So we can do some functional derivatives. We just derive everything from the functional, and we can introduce brackets. So for mathematics, it's just two forms. So for example, we have the Poisson bracket, which will be the analog of the canonical symplectic form. So this is just the basics, but now we want to extend the usual geometry of this dynamics. So when we start for just a particle and we want to describe dynamics in a phase space just from basics analytical mechanics, we have this phase space of position and impulsion, we have our Hamiltonian, we have our canonical bracket, and then we can describe the dynamics of any functional, so any function on the phase space, which can be a physical observable just by applying this bracket with the Hamiltonian. And we have the thermodynamic principle, which is that the energy is preserved. So at this point, it is the usual Hamiltonian dynamics that you all know. But now what I want to do is to generalize a little bit. So well, this is just the generalization to any Hamiltonian with any form, of course. I will go directly there. So now we want to include some dynamics. So for that, we start again from our phase space, and we start again from a functional. But now, rather than just considering energy, the Hamiltonian, we'll include entropy to be able to do some statistical physics above it. So for this, we will replace the usual Hamiltonian by the free energy, which is the difference between Hamiltonian and entropy. And now we will define a more global bracket. So it will no longer be a Poisson bracket, but we can add a dissipative part, which will be a symmetric bracket, so a metric. So now we have this new bracket, which is at this point a very generic two-form application. And then now we want to describe the dynamics of a functional, so the dynamics of an observable. So we want to do something very similar as previously. And so for this, we can just say that for any function f, its time evolution, its dynamics, will just be given by the bracket taken between itself and this new functional, the new free energy. So of course, this is very similar to the previous and usual Hamiltonian dynamics, but now we add some degrees of freedom because we have this more general bracket, which will introduce a symmetric part. And now we would like to have some thermodynamic principle. We would like to conserve energy, and we would like to increase the entropy because this is what we expect from a physical system. So for this, we will make some hypotheses on our bracket. So firstly, we have for any physical system that the entropy is a Casimir function of the Poisson bracket. So if you take the entropy in the Poisson bracket, so the usual Poisson part of the bracket, it will always give you 0. But now we want to do something symmetric, and this is the metriplectic condition. We want that the dissipative part, the symmetric bracket, when taken on the Hamiltonian, will give you 0. So it means that when you are doing just thermodynamics, this thermodynamics will not change the energy at all. So if you have this, the dynamics is very much simpler because you can decompose your global equation into two parts. The first part when you take the Poisson bracket on the Hamiltonian, and the second part when you take the symmetric bracket or dissipative bracket on the entropy. Yes?
Still assume Jacobi identity for the
Poisson bracket, yes. So now if you have this decomposition due to this property, you can write thermodynamic principles, which are very nice, because you have the Hamiltonian is indeed conserved once again. Its evolution is just 0. And now when you look to the entropy part, because it's a Casimir function, the Poisson bracket do not apply. On the symmetric part, you just have the symmetric of a function taken on itself. And so if you assume that this bracket is symmetric and positive, which we'll now do, we will have that indeed the entropy is always growing. So you create entropy by dissipation, but you can never reduce the entropy, which is a physical expectation for your system. So now you have just generalized the usual Hamiltonian dynamics by extending this bracket, and by doing so, you are able to have new dynamics when you will have an entropy increasing. And of course, geometrically, it will change a lot of things because you are now in a path where you will increase entropy to a maximum of entropy and then reach this quasi-Coulomb state. So now that we have said this, we want to do some physics with that. So let us discuss just 1 minute why is the physics in these models. Because there is the geometry, which is the mathematics, you are all interested in this part. But as a physicist, I want to know where is the degree of freedom when I can put the physics of my system. So of course you have the Hamiltonian. The Hamiltonian describes all the physical interaction in your system. So it's a generic function mathematically that I can choose as a physicist to describe a particular system. Then there is the Poisson bracket. But this actually is purely geometrical because it just comes from the canonical symplectic form, and so there is a mathematical canonical natural way to define it. There is no degree of freedom for the physics to apply in this Poisson bracket. So now what about the dissipative part? Well, actually the entropy is just the coupled thermodynamic, just coupled by the thermodynamic identity, but it is geometrically just an additional direction that you need to add into your phase space. You need to add this as a new degree of freedom for your phase space, but it is just a geometrical dimension. There is no physics really into this definition of entropy, which is just purely formal. But however, in the dissipative bracket, well, here you will be able to play some physics. Because this dissipative bracket, it will have directions, and it will have eigenvalues, and these eigenvalues, they will be related to the transport coefficients that you will have from your physical system. So as a physicist, you want to choose your Hamiltonian, and you want to choose your dissipative or symmetric bracket. These two degrees of freedom are where the physics will play. And these two other degrees of freedom, the Poisson bracket and the geometrical entropic direction, which is coupled by just thermodynamic identity, these are purely geometric, and so just a playground for doing mathematics on it. So this is a formalism which was introduced a few decades ago now, but until now, this was purely generic or general, and applied to very few physical systems, where just on this physical system, we found a way to express it into this nice geometrical form. But now we want to do something which is more generic, which is more systematic, and so we want to be able, from a physical system, to produce what will be the associated dissipative bracket, to then be able to do physics more generally with this kind of geometry. So now we want now to understand the thermodynamic theory for this dissipative bracket. So from a thermodynamic point of view, you can always describe a system just by a given of just few variables, which will be conservative quantities in your system, and then you give yourself a thermodynamic identity, which is just saying geometrically the direction of entropic growth given the variation of the variables. So this is just adding a constraint to define the entropy in your system, and you can always define an entropy from the thermodynamic identity. And because you have conserved identity, you expect physically to be able to write a conservation equation for any of these variables.
What is sigma?
Sigma is the entropy, it's a local entropy. So the entropy, it can be defined locally from a volumic point of view, or you can define the global entropy, which is the integral of this value sigma, which will then be the total entropy of the system, which must grow from a physical point of view. But the local entropy can be decreasing locally because you can exchange entropy with you. We want to describe a fluid-like model. So if you have conserved quantity, you can define an equation for this evolution of quantity, which will bring you, because it's conserved, to introduce a flux, because you cannot create or destroy any of this quantity. You can only exchange it with your neighbor, so you have a flux of these quantities. But up to now, this can be a very generic function. There is no constraint at all. But now, from when you're doing simplest physical models, but actually it's applied to very generic models on most of physics we do nowadays, it's to do just a linear response theory. In linear response theory, you will make assumptions about the fluxes, so how the quantities in your system will evolve. Well, they will evolve linearly because it's small perturbations, you are close to equilibrium, from the different affinities of forces which are just the gradients of the quantity. So for example, if you have a gradient of density, you will introduce a flux of matter. If you have a gradient of temperature, you will introduce a flux of energy. If you have a gradient of electric potential, you will introduce a flux of charge or current, electric current. So this is just the usual physical way to describe the thermodynamic evolution of a system which is not uniformly at equilibrium. So now if we have assumed this kind of linear response theory, we have just an expression for these fluxes as a function of the different, sorry, I was on the wrong side. We have just an equation for the fluxes as a function of the gradient of infinities with just some matrix, which is just a linear combination of the different fluxes. So now we have this matrix L, and we can say a little bit of things about these matrices from physical grounds. So this matrix, which relates the fluxes as a function of the forces, of the gradient of quantities, well, physically you can say some things. You can first say that it is a symmetric matrix, and second that it is a non-negative matrix. So why? So first, a symmetric matrix, it's come from microeconomical quantities. When you're doing statistical physics, you know that at the microscopic scale, all equations of motion are reversible in time. On this microscopic symmetry, time reversal symmetry, you can show that it comes at the thermodynamic level as the symmetry of this matrix. And second, it's non-negative. This just ensures that you have the growth of entropy. If you have negative coefficients, you could decrease the total entropy, which is not allowed by physics. So L is symmetric, non-negative. So now it's very nice because it's already starting to look like a symmetric and positive bracket. So actually, you can just rewrite everything. So I don't want to go in the equation, but just to highlight that it's very simple computations, as we like in physics. When you have the equations of motion for any properties, we start from just equation of motion, which is conservation motion. We know that it comes from a flux. Well, this flux, we can just rewrite it from linear response theory. And now we can rewrite everything into a functional form. So we just add integrals. And from this, you can just try to symmetrize the whole, and then you will just get something which is very nice because it's now looking like a bracket applied to any function of your phase space. So this now will give you a bracket, and this bracket is symmetric and non-negative. So it's non-negative because, as you see, it will get you squared when you have twice the same thing, and L is a non-negative matrix, and it's symmetric because we have been able to symmetrize everything. On this matrix L, we know from physical grounds that it will be a symmetric matrix. So we have this new bracket. And because we have this, you can write the evolution equation, not only from the basis, which was the choice of conservative variables, but because everything can be written from it for any functional of your system. So if you are doing non-equilibrium thermodynamics, which is what we do usually in physics, in, for example, Navier-Stokes equations with viscosity, in Fourier equations for the temperature, etc., etc., we can just rewrite it in the phase space as a symmetric bracket, which looks like that, and this will give you the thermodynamic evolution, so the dissipation dynamics of your system. So now we understand the origin of this dissipative bracket. We have first added it just geometrically to be able to describe the kind of system we wanted. Now we just understand that it's a direct application of non-equilibrium thermodynamics with linear response theory. So this dissipative bracket is natural, and you can, for any physical system, write it explicitly. So in particular, we have a systematic way to write it from the model you want to do in physics. And we can note that in this bracket, it has a very simple form as we wrote it, but not in any variables. In the variable, so in the map, where you have chosen the variable as coordinates, the functions which are conserved quantities of your system. If you go for any other function, then the bracket will not look as nice as the one I wrote. And in particular, in thermodynamics, energy is a usual conserved quantity. So you want to use energy as a variable. But when you are doing dynamics, you don't want to use energy as a variable. You rather want to use entropy, which is a conserved quantity for the dynamical part, as a variable. So there is two sets of variables, a set of variables in which the dynamical part is simple to write, you get the canonical bracket, and a set of variables where the dissipative part is easy to write, you get a very simple form for the bracket. Of course, everything is geometric, so you can go from one set of variables to another, but at the end, you want to choose a set of variables where everything will be the simpler to write, and it is not the same for each part. So if we now want to do an applications, we can apply this, for example, to Navier-Stokes equations, which is a very simple system. So this is just a rewriting of Navier-Stokes equations, where I put an equation for entropy directly. It's just a rewriting of the usual equations, including the Fourier part. So you have some temperature which can vary in your system. It's allowed in this system. So you can rewrite these usual equations. And this cannot be written into an Hamiltonian way, because in an Hamiltonian way, you will not have any dissipative terms, which are crucial here. So now let's try to write into a metriplectic formalism this kind of dynamics. So first, we will identify a set of variables which is nice for us. It will be the energy, so the local variables associated to the Hamiltonian, but also the momentum, quantity of momentum, which is always conserved in physics, and the quantity of mass, so the mass density, which is also a conserved quantity. So given this set of variables, you can easily write your bracket. But first, you need to know what are the relation between these and entropy. This is what we call in physics the thermodynamic identity, which is just the geometric identity which gives you the direction of entropy when you know the direction of variation of everything. So for this, we start by rewriting the total energy of the system. So you have kinetic energy and you have internal energy. So U is the internal energy of your fluid, which gives you an equation of state for your fluid. And from this, you can just now write the evolution of these internal variables that you know from usual basics thermodynamics. And then this gives you an identity for the entropy. So you can write that the variation of entropy is given first by a variation of energy and second by a variation of momentum coming from the kinetic energy that you have in your Hamiltonian. So now that you have this, you can write what are the different conjugate variables. So what are the forces associated with the fluxes. So now you can do it. You can write the canonical bracket that we wrote before for the dissipative part, and you can rechange variables just to go back to the usual dynamic variables where you change energy for entropy. If you do that, you can just change variables for your bracket, and you will get a bracket, and this is a dissipative bracket for Navier-Stokes. Of course, we already know the dynamical part for Navier-Stokes, just Hamiltonian dynamics. So if we put these two parts of the bracket, it will give you a global bracket. And using the dynamics following this bracket, you will get exactly in your phase space the dynamics of your fluid in following the Navier-Stokes equations. So you can also do it for MHD, but I will not go more in detail, I think, because I will not have the time. So we can write everything. We can write everything for MHD too if we want to do plasma dynamics. So for any physical systems, we can write this kind of dynamics. So globally, what we have seen is that there is an Hamiltonian, or at least Hamiltonian-like way to write geometrically the dynamics of systems like MHD or Navier-Stokes. So it is nice because we can extend these geometrical tools to apply to many more physical systems of interest for applications. So this is something quite interesting. So we have this bracket. We can. It was already known for Navier-Stokes from just guessing, but we refound it from our generic formalism, but we can now apply to any other system. So of course, by construction, you also have conservation equations. So in particular, conservation of mass, momentum, and energy, but also magnetic field if you are doing plasma physics, are interestingly conserved into your dynamics, they are constant of motion, and additionally, you will always have indeed the entropy which grows until you have attained your maxima. So this was for the first part. It was the first way to try to introduce dissipation into this system. But quickly, I would like just to discuss another way, which is completely different. And now we don't want to change the bracket, so the symplectic form, to add something which is not symplectic, but rather we want to introduce some singularities into the bracket. So for this, we can use what is called B geometry. So if you have a B manifold, it means that you have a manifold and you have an hyperspace on which you will basically allow your symplectic form to be divergent. So it is just punctual. So above integration, it's not a big deal. And if you do it properly, you can control everything. So this, I leave you to go more into that. You are probably more expert than me in this kind of geometry. So globally, we can do some geometry with this kind of systems. We have an Hamiltonian-like system where we just have a symplectic form which is no longer canonical, but which includes some divergences. So for example, here you have a local writing of this, where you see that in the variable f, you will have a divergence of f equals 0 in this hypersurface. But anyway, you can still be doing geometry everywhere. There is no big deal into it. So, so we can write a usual b-symplectic form. So there are two ways to write it basically. You can either put the divergence into the position variable, so in the Q's, or into it's what we call non-twisted form, or in the momentum variable, so in the P's, you will call it a twisted form. So from a usual configuration space, you get your phase space, and you have two ways to write this canonical b-symplectic forms if you want to do some b-geometric geometry. And you can do everything you can do with symplectic geometry, basically. So now let's try a little bit. We start from very simple. We start with the Hamiltonian of just a point object. So we have some kinetic energy plus some potential F. So let's look to what is happening if you just put a singularity into the system. So we can write the usual Hamiltonian flow associated to that, but now using this singular symplectic form, and here we will use the twisted one. If you do so, you will get a new set of variables, which are no longer the usual Hamilton's equations, but you will get corrections coming from this singularity, and you see that you get this set of equations. And if you rewrite it directly as an equation of motion for the position, you get something looking at that, which is not at all the usual equations of motion you expect for a physical system, but actually that's still something very interesting, because you see that now your acceleration is proportional to minus something times the velocity. So it's just the usual way to write some dissipation. So you see from this just first naive try that you, by including some singularities, you can introduce some dissipation. So of course you can control the coefficient of dissipation by this potential F that we have introduced first. But of course that's very ad hoc. We have just tried this for just one particle in one dimension. That's not very general. But we have started to understand something, which is that singularities in symplectic form can be a way to introduce some dissipation in the effective physical system. So you can write, as usual in geometry, flows. You can follow your flow. And now your singularity at Q equals 0 here, they will give you a point in which you will never come back. You will come back closely and closely to this point. And this is just because of dissipation, you slow down your dynamics. And now you have a point you will never reach because of this. So now let's try to generalize a little bit this. So we have this, that this singularity can introduce some dissipation. Let's try to generalize this to more generic and higher dimension systems. So for this, we start from a physical system. We have a configuration space Q. We have the usual phase space to do that, but we will add new dimensions. In the configuration space, you will add a new coordinate for time, which will no longer be the geometric time. So there is a physical time, which is a coordinate, and there is a geometrical length, which is no longer a priori the same as the physical time. If you do that, you get in the phase space a second dimension that physically you want to interpret as energy, the conjugate variable of time. And now, if you write the Hamiltonian, you want your Hamiltonian to be something which is physically conserved. Well, you just can write the usual Hamiltonian minus the energy of the system, and this should be 0 if you have a realistic physical system. What we have done here is that we have introduced additional dimensions to introduce new degrees of freedom. So of course, this is a trivial equation to write that energy equals energy, but if you do that, you write it into a geometric way, where you will get more dimensions to write your dynamics, and then you will project on the physical part, which is what you will be interested in at the end of the day. So now we want to use symplectic form, adding these dimensions. So we can, from the canonical form, just add new part for this new time and energy. And now if you write the equations of motion, the usual one, you will get something which is very simple and natural physically, which is the usual equations of motion. And you will just tell that the time derivative is 1, meaning that the physical time equals the geometrical time, and that the variation of energy is just given by the due to the variation of the potential you apply. So up to now, it is exactly what we expect physically to get. But now let's play a little bit with that. Let's do some rescaling of everything to be able to get something which looks Hamiltonian, but which is dissipative at the end of the day. So for that, we will rewrite a little bit our Hamiltonian. And if you do, and we will get, we rewrite the little bit the Hamiltonian, because we want at the end of the day to get some dissipation with some coefficient lambda. So we want our dynamics to be slowed down at a speed lambda. So as much as you slow down, everything is slower. So to compensate, you need to accelerate time to get something equivalent. And it is exactly what we will be doing at the end of the day. So we have this set of equations for Hamiltonian equation. And now, because of this new way we have introduced rescaling of time into the Hamiltonian, you see that the physical time t has an equation of motion which is non-trivial, meaning that it is no longer equal to the geometrical time that you have in your system. But this actually is very nice, because if we rescale all of this, you can go into a symplectic form, because you will just get a log into the new definition of your time. And if you rewrite the dynamics of your system, you get that indeed the equation of motion is the one you expect, with the usual potential which drives your system, plus a dissipation part with the coefficient lambda. So all of this for what? Well, we have been able to write an equation of motion of something which is dissipative. You have dissipation in your system, just by rescaling everything in the Hamiltonian. On this, we have seen that it is actually exactly the same as a very simple system where you don't need to rescale your Hamiltonian, just by going to a singular symplectic form. So if now we start again from this symplectic form, where you have this time s in which you put a divergence, so you have an extra dimension on which you put a dimension, and you reinterpret it as a physical time, well, then you will have the slowdown of your dynamics. So at the end of the day, if you put a time dimension in which you put a singularity, you can introduce dissipation in your whole system, and solving your system as just an Hamiltonian system into a higher dimension system and then project it, you will be able to write dissipative trajectories into an Hamiltonian and then conservative way at higher dimension. So globally, we pay the cost of higher dimension and so more complexity to add some to get some dissipation into our system. But what is nice here is that we keep an Hamiltonian way to write everything up, maybe to add some singularities. So we have these two ways. Either we rescale everything in the Hamiltonian, or we add some singularity in the symplectic form. This is actually equivalent, but we have two ways to do this kind of dynamics. So on this, I would like just to conclude. In the first part, we have seen that we can add dimension. You can add the dimension in your brackets. You can allow a symmetric part in your bracket and then introduce some dissipation. This applies to any system of physics which is non-equilibrium with linear response theory. In the second part, we have seen that we can, just by adding a time dimension on a singularity on this time dimension, which is equivalent to a rescaling of all the times, we can just get by this way a global dissipation of your system, and then it is another way to introduce some dissipation in Hamiltonian system. And on this, I would like to thank you, and I hope that maybe you will do some physics with that.